Hello, STAT students. Today we will do our last section of the semester. We'll be talking about geometric distributions. The last couple of times we've been talking about binomial settings and binomial distributions. In a binomial setting, the number of trials n is fixed and the binomial random variable x counts the number of successes. In other situations, the goal is to repeat a chance behavior until the first success occurs. These situations are called geometric settings. A geometric setting arises when we perform independent trials of the same chance process and record the number of trials until a particular outcome occurs. The four conditions are very similar to the ones for binomial distributions, or the binomial settings. With binomial settings, you have the bins that we talked about. Well, for the four conditions for geometric setting is bits. So the binary and the independent stays the same. For the binary, the possible outcomes of each trial can be classified as success or failure. For I independent, trials must be independent. That is, knowing the result of one trial must not have any effect on the result of any other trial. Here's the difference. Instead of having the number of trials as fixed as we did in a binomial setting, the goal is to count the number of trials until the first success occurs. You know, it might be better to just call this BIFs for first, and you could totally do that if you want to. And finally, the success is still the same. On each trial, the probability P of success must be the same. All right, for geometric random variables, the number of trials, y, that it takes to get a success in a geometric setting is a geometric random variable. The probability distribution of y is a geometric distribution with parameter p, which is the probability of a success on any trial. The possible values of y are 1, 2, 3, 4, so on. Okay, on your formula sheet, this is the formula that is given for geometric distribution. And so it's the probability, your geometric random variable is x equals, and then you have this lowercase x. And before, in the old ways, it used to be k's, and it really doesn't matter what that little variable is. And that was equal to 1 minus p, which is the failure, the probability of failure, to the x minus 1, because it's all the way up to x. And therefore, so if you have, say, x equals 10, then the failure would be whatever the probability is to the 9th power, and then your success would be the last one. So times p. And so that is on your formula sheet. And it even tells you that it's for geometric distributions. Note, like binomial random variables, it is important to be able to distinguish situation in which the geometric distribution does and doesn't apply. Okay, let's do a sample problem. A student will be selected, this is called a birthday game. A student will be selected at random from the class and asked to guess the day of the week on which one of the teacher's friend was born. If the student guesses correctly, then the class will have only one homework problem. If the student guesses incorrectly, the teacher will again select a student from the class at random. This student will try to guess what day of the week a different friend was born on. If they get it correct, the class only has to do 2 problems. The random variable of interest in this game is y. Y equals the number of guesses it takes to correctly identify the birthday of one of your teacher's friends. What is the probability the first student guesses correctly, the second, the third? What is the probability the X student guesses correctly? Verify that y is a geometric random variable. So this is all pretty much done, but we're verifying. So success is a correct guess. Failure is an incorrect guess. For independent, the result of one student's guess has no effect on the result of any other guess. Therefore, you have a different friend. For T, we're counting the number of guesses up to and including the first correct guess. And S, on each trial, the probability of a correct guess is 1 out of 7 because there are 7 days in a week. Right. Calculate the probability when y equals 1, y equals 2, y equals 3, and y equals x. So y equals 1, so you would get 0 wrong. You're correct on the very first try. And so the probability is 1 out of 7, which is 0.1429. For y equals 2, the first one is wrong, and therefore the correct is 1/7, and the two should add up to one whole. So this is the correct, and then you have first wrong. Okay, for y equals 3, the first two are wrong, and the third is right. So 1 wrong, 2 wrong. And that's where the formula comes about. So it's 6/7 to the second power and 1/7 to the first power, and multiply those, and that will give you a probability of 0.1050. Notice the pattern. So here's our formula. So in this particular case, I'm using y as your variable. So y equals k. So we're talking, so y equals x, sorry. So because it was the x student. So this would be 1 minus p. So the failure, probability of failure to the x minus 1 times the probability of success. Here we go. And that's your formula. But on the formula sheet, it's just capital Y, x equals little x. But the process is still the same. Let's do some example problems. If y has a geometric distribution with probability of p of success on each trial, the possible values of y are 1, 2, 3, etc. If x is any one of these values, so this is just the formula again, 1 minus p to the x minus 1 times p. Here's the sample problem. In the board game Monopoly, one way to get out of jail is to roll doubles. So doubles, are 2 1s, 2 2s, 2 3s, 2 4s, 2 5s, 2 6. So there's 6 out of 36 that are doubles. So that's 1/6. So the probability of rolling doubles is equal to 1/6. Find the probability that it takes 3 turns, so exactly 3 turns to roll doubles. So in that particular case, the probability for x equals 3 is equal to, so using the formula, the first two, so you could say 5 6 times 5 6, or 5 6 to the second power times 1/6. Because you have your 2 failures before you have your success. And you multiply that out and you get 0.1157. You could do this on a calculator as well. So like we had, depending on the calculator you have, I don't believe the TI-83s have the geometric PDF. And because this is an exact value, you would use a PDF. And you only have, instead of having all those prompts that you did for binomial, you would only have 2 prompts. And the first prompt is probability. Which is 1/6. And then your point would be x equals 3. In parentheses, 2 close together. But anyways, that'll give you the exact same answer, 0.1157. So you could do it either way. Part B, find the probability that it takes more than 3 turns to roll doubles and interpret this value in context. So this particular one, if you're doing anything that's greater than, less than, so on, you're going to use the and you're using a calculator, you want to use geometric CDF. In this case, greater than 3 would be 4 turns, 5 turns, 6 turns, 7 turns, but not 3. So you want to subtract anything 3 and less from 1. And that's where that comes in handy. So you want to do 1 minus the probability that x is less than or equal to 3. Because remember, you don't want 3, 2, 1. Anything less than or equal to 3 you don't want, but you want anything greater than 3. So you want the 4, 5, 6, 7, 8, 9, whatever. So that would be 1 minus your geometric CDF. And remember, to get those, to get to that particular menu, you're going to go to second, and then you're going to go to vars, and then you're going to go all the way down until you see geometric CDF. And so your probability is 1/6 probability of success, and your value is going to be x is less or equal to 3. So you're just going to put x equals 3 there. And that'll give you an answer of 0.5787. And so let's interpret this. There is a 57.87% chance that it will take more than 3 turns to roll doubles. And that's how you do that particular problem. There are also means, which are the expected values of geometric random variables, and this is on your formula sheet, as is the standard deviation. We're not going to talk about the standard deviation in our notes, but the formula is on your formula sheet as well. So the expected value of y would be equal to, so for the binomial random variable, the expected value was n times p. So for this one, it'd be 1 over, because there is no such thing as n, there's not a fixed number of trials, so it'd be 1 over p, and that'll give you the expected value or mean of a geometric random variable. Let's do a sample problem. In the board game Monopoly, one way to get out of jail is to roll doubles. If this was the only way to get out of jail, how many turns would it take? It's weird. How many turns would it take on average? So the mean of, well, I guess we'll call it y, is equal to 1 over 6, or actually it was x, because that's what we used in our, it doesn't matter. So 1 over 1/6, and so remember, that's the same thing as 1 times the reciprocal of 1/6, so 6 over 1, which is just 6. So the mean of x equals 6 turns. And let's just interpret this because it's good practice. On average, we would expect it would take 6 rolls to get at, or turns or whatever, to get out of jail. You could be like me and just when no one's looking, just do something. So that's how I always win. All right, determine whether each random variable described below satisfies the conditions for a binomial setting, a geometric setting, or neither. Support your conclusion in each case. So let's look at example A. Draw a card from a standard deck of 52 playing cards, observe the card, return the card to the deck, and shuffle. Count the number of times you draw a card in this manner until you observe a jack. So I look at some keywords here. You're returning the card to the deck, so that meets the independence. So I'm going to put an I here. You count the number of times you draw a card until you observe a jack. So the keywords here being until. When you see that, you're going to keep doing something until you get that success. So that is going to be the T part, drawing until you get a jack. I would just go ahead and see what we can come up with. So for B, for binary, it's success, you get a jack, failure, not a jack. For I, it meets the independence condition because you replace the card. Okay, here we knew it was geometric because it says you're going to draw until you get a jack. And lastly, the probability of success. So the probability is 4 out of 52, or 1/13. And so we know this is a geometric setting. All right, next one. Joey buys a Virginia lottery ticket every week. X is the number of times in a year that he wins a prize. Okay, so B, success equals wins a prize. Failure doesn't win. Is the independence condition met? Well, buying one ticket is independent each week. Okay, N. Well, the reason why I'm going to say N is because it says, notice it says buys a ticket every week, so N will be 52. 52 weeks in a year. And then lastly, the success of probability will be the same each week. This is a good review of binomial as well. It's binomial. So that was a good review. Now let's do two sample problems on geometric distributions. Suppose that 20% of a herd of cows is infected with a particular disease. What is the probability that the first diseased cow is the third cow tested? Not the first, not the second, but the third. So that's probability that X equals 3. So you're going to do it, keep repeating it until the third time. So this is going to be a geometric pedia, it's exact, and your probability is 0.20, and your X equals 3. Go to second vars, put in your calculator, and you get the probability that probability X equals 3 is 0.128. If you didn't want to use a calculator and you wanted to do it by hand, well, I mean, you'd still use a calculator to multiply it, but if you didn't want to use the second vars, the distribution menu, you could use the formula on your formula sheet. So that'd be 0.8, first one is a fail, and the second one is a fail, so 2 fails. On the third one, the success would be 20. You would get the success would be 0.20 on the third. So the probability is still the same. And that would be 0.128. So it doesn't matter how you do it. You could do it either way right there. Part B, what is the probability that 4 or more cows would need to be tested until a diseased cow was found? So the probability for x's, and 4 or more means including 4, so greater than or equal to 4, you are going to subtract what you don't want. So 3, 2, 1. So you want to subtract off that. So 1 minus the probability that x is less than or equal to 3, because you want to include 3 and everything below that. So when you subtract from 1, that is, to get the probability that x is greater than or equal to 4. So 1 minus the geometric CDF, your probability of success is 0.2, and x is less than or equal to 3. Put that in your calculator. Remember to put the 1 first, and then put the 1 minus, and then go put in all your stuff. So that would give us the probability that x is greater than or equal to 4 is equal to 0.512, so 51.2%. Okay, last example. Research suggests that about 24% of 12-year-olds in the U.S. can pick out the state of Colorado on a map. A, what is the probability that you must sample exactly 5 12-year-olds to find the first one who can pick out Colorado on a map? So until, we see that word until, or you must have to find the first one. Yeah, so if you see something like that, you keep doing it until you get that success. So the probability, this is exact, so x equals 5, is equal to geometric PDF, probability of success is 0.24, x equals 5. And that will give us 0.081, or I'm sorry, 0.0801. So that's your answer. And again, if you wanted to do it the old-fashioned way, using the formula on the formula sheet, that would be the failure. So if 0.24 is a success, failure is 76%, and that'd be to the 4th power, because it would take 4 to guess incorrectly or to not get it right until they can pick it out, until the 5th one gets it right. So times 0.24, and that'll give us the same answer. You don't have to do it both ways. I'm just kind of giving you the option of which way do you like better. And it works when it's exact, though. What is the probability that you must sample 5 or more 12-year-olds to find the first one who can pick out Colorado on a map? So x is greater than or equal to 5. So subtract probability that x is less than or equal to 4 from 1. So it'd be 1 minus the geomet CDF. Just remember, C is for cumulative and P is for point. So probability success is 0.24. X is less than or equal to 4. And therefore, the probability that x is greater than or equal to 5 is 0.3336. And for tonight's work, you'll be doing some practice problems that will help you differentiate between binomial and geometric. So hopefully you have a better understanding of those two types of distributions. That's all the notes for today. Have a great day, stat students.